we're going to knock out 3 problems. We're not really doing much in any of the problems. The last one we will. Okay, let's go get it. So here we go. We're just going to go find the length of the curve. F of x is equal to x squared. That parabola is centered right there at the y, centered around the y-axis. And closed interval from 0 to 2. Then we go through and we're like, well, let's go find our derivative. Let's just get it done now. And then let's square up our derivative. And we get 4x squared. Cool. So the length of our arc from 0 to 2 of the square root of 1 plus, and then we put in our 4x squared dx. Neat. Now solve it. Oh, wait a second. Come on, look at it. What are you going to do? You're going to U sub? I don't think so. Can we use power rule? No, I don't think so. We don't have the techniques to solve this yet. We just don't. Soon we'll learn some things called a trig sub, and a trig sub actually doesn't work here either. But a hyperbolic trig sub, I think that would work out cool. Or a hyperbolic trig. A hyperbolic substitution, that would end up working out. But we don't have those techniques yet. We can also do it by an approximation, but we haven't learned those techniques either. So what we're seeing is sometimes they have to be cooked up. What is that, the 5th time, 6th time I've used that term? We're going to continually have problems that they have to be set up in such a manner for you to be able to solve them. This isn't going to work for us. I can tell you it's like approximately like 4.647, but how the heck would we get to it? So sometimes we might want to change things. We want it to look a little bit different. Meaning, we may want stuff in terms of y's instead of in terms of x's. Because if it works for x's, it's going to work for y's. It's changing up our orientation. It's the same gosh darn formula, except now we're saying 1 plus a function of y's derivative squared. And going from some c to d, some y value c to some y value d. So let's go take a look at our next problem. So we're going to find the length of the curve f of x is equal to x to the 2/3 power between x equals 0 and x equals 8. And if we just try and set it up as such, from going from 0 to 8, let's go find its derivative. I'm sorry. So 2/3 x to the negative 1/3, and then when we square it up, what are we going to end up with? That's like 1 plus 4/9 x to the negative 2/3 power dx. Yeah, go ahead. Solve that out for me, please. I'll wait. Yeah, we don't have a tactic for it. It's not cooked up in the proper way. And don't worry, I'm not doing this to you on test. I'm not going to set it. I'll give you stuff that's cooked up, and you just have to know the way to get around it. But I just want to make the point that sometimes it's easier to do things in terms of y. So don't stress too much of the thinking like, I got to make sure that I can change it. Arc length is what it is. I'll give you something cooked up and you'll be able to run right through it. But this is a great time for us to get practice with seeing it. So let's say y is equal to x to the 2/3 power. And let's solve for x in terms of y. So we're just going to raise it to the 3/2 power. And we can say y to the 3/2 is equal to x. So there's some g of y. Some g of y is equal to y to the 3/2 power. And hopefully you've been paying attention in the last few videos and you go, oh, geez. We're raised to the 3/2 power. Our second video, our first problem we actually did, it had an x to the 3/2 power. This is going to work out. It's cooked up in such a way that we can solve. So let's take our length of our curve. We'll deal with the bounds in just 1 second. And now we can do 1 plus whatever our derivative of g squared is going to be. And this should seem fairly familiar to you. So g prime of y is equal to 3/2 y to the 1/2 power. Then we need to square it, and we're going to get 9/4 y. I swear we've done this problem before. We have. It's going to work out. Now, what do I do? Just pop in 0 and 8? When everything's in terms of x's? Heck no, we can't do that. We can't do that. We can't do that. So what we want to choose is right from back here. We know that y is equal to x to the 2/3, so let's solve for our y values. Let's go get those values. So let's start with when x is equal to 8 to the 3rd power. Then y is equal to 2 to the 3rd power. Oops, I have that backwards. It's 2/3. I'm sorry. I keep thinking of the 3/2. And then the 3's are going to cancel out, and you're going to get the y is equal to 4. 2 squared. There's our top bound. And then x equals 0. Y equals 0. I'm not doing anything else in that. So now we're taking the integral from 0 to 4. The square root of 1 plus 9 fourths y. This is the same problem now. All you'd have to do is just change the letters from y's to x's, and you're going to get the same gosh darn thing. You do your quick u sub. U is equal to 1 plus 9 fourths y. Du is equal to 9 fourths. dy, you get your 4/9. Du is equal to dy. We'd go through, we do the substitution. But this is the exact same problem at this point in time that we did in the second video, where this is just going to turn out to be, what is this? Sorry. Give me just a moment. That's going to be 8/27, 10 to the 3/2 power minus 1. Because we've already done this problem. It has to be cooked up. So we're looking for those 3/2 powers. We know that we're going to pull something off if we have an x to the 3/2 or a y to the 3/2. Even with a constant in there would be a good. That's the setup. But again, on tests, I'm not trying to trick you on this. If I tell you to go find the arc length and it's all in terms of x's, just leave it in terms of x's. I'm not going to be that much of a jerk. Unless I forget, of course. Sorry. No, moving on. All right. Oh, shoot. No, you didn't see that. You didn't see that. I forgot to take that off. All right. Find the arc length for f of x is equal to the natural log of x plus the square root of x squared minus 1 on the interval, closed interval, of course, 0 from 1 to root 2. And if you saw what I just erased, then maybe you understand where we're going to go with this. Because good effing luck. See, we have an f. That's why I said effing. Take a derivative on this. This ends up becoming 1 plus, that's the square root of x squared minus 1. Yeah. And now we're going to square it and put it in a square root. Yeah, good luck. Good luck. Leaving it in terms of x's is not going to be a good example. Now, hopefully, your Calc 1 teacher spent some time in hyperbolics with you. And even if your teacher did spend time with you with hyperbolics, there's a good chance you probably forgot most all of it. This is equal to inverse hyperbolic cosine. Clearly, right? Clearly. So possibly, we could just do a little trick. So we could say y is equal to inverse hyperbolic cosine of x. That's why we call it cosh, because it ends up being a lot of talking. And well, let's solve for this so we get x equals. So all we have to do is just, since it's cosh inverse, hit it just with a cosh on both sides. And then we end up with hyperbolic cosine of y is just equal to x. So we could call it some g of y is equal to hyperbolic cosine of y. Ooh, there we go. So let's think about our arc length. Oh, we changed it to y, so we can't choose these. Oh, well, we'll be all right. We'll be okay. I'm sure of it. We're going to take the square root of 1 plus, and oh, we have to take the derivative on this. So g prime of y is equal to inverse, or not inverse, why do I keep saying inverse? Hyperbolic sine of y. And then we're going to square it up. So there we are. But we're still going to need to change our bounds. So this is y is equal to. So let's say when x is equal to 1, what do we get? Natural log of 1 plus the square root of 1 minus 1, which is just 0. So this is the natural log of 1. Oh, it's 0. That's not a bad bound. And now when x is equal to the natural log of 2, or not the natural log of 2, it's the square root of 2, sorry. Kind of know where this is going to go, and the square root of 2, we now have the natural log of the square root of 2 plus root 2 squared minus 1. Square root of 2 squared is equal to 2, and 2 minus 1, oh, this is the natural log of the square root of 2 plus 1. How clean, huh? Isn't that just such a nice, clean... No, that sucks. It's gross. And we changed our bounds. Now, we could do all of this with e to the x's, and you could have run through this and found the inverse the way you want to find the inverse to find out that this is actually equal to... Never mind. I'm just going to stop. All right. I want to teach everything. We're 11 minutes in. Let's finish this thing up. Now, we have this fundamental hyperbolic identity. It's a hyperbolic identity. Just like you remember from trig, sine squared plus cosine squared is equal to 1. Well, we have an identity with hyperbolics. And if you just know this one, I think you can get everything from it. And it tells you that cosh squared of x, or y, doesn't really matter, minus sinh squared of y is equal to 1. So if we add this over to the other side, we have exactly what's underneath our radical, in our radicand. So we can go through and change this. The integral from 0 up to the natural log of root 2 plus 1 of the square root of cosh squared of y dy. Fortunately, hyperbolic cosine of y or x is always positive. It makes no freaking difference. So we don't need an absolute value or anything weird like that. So we're going to get the integral from 0 up to the natural log of the square root of 2 minus 1 of just cosh of y dy. And the derivative is, or the antiderivative is, the same thing as the derivative. So it's 0 to the natural log of root 2 minus 1. Neat. So what's the answer? Could you do this? Well, sinh of y is e to the y and the e to the negative y, all times a half. If we evaluate from 0 up to the natural log of root 2 minus 1, let's see what we get. So there's going to be 1/2 e to the ln of the square root of 2 minus 1 minus e to the negative square root of 2 minus 1. So I'm going to cheat now. I'm going to do it. I'm going to take that, we're going to raise this to the negative 1/2, 1 power. And then we have to subtract out our e to the 0th minus our e to the 0th. That's 1 minus 1, and that just goes away, right? Just whack. Goodbye. Goes to 0. So now we can see that cancels. We have 1/2 times the quantity of the square root of 2 minus 1. Minus, these are going to cancel, but now we're left with the square root of 2 minus 1 raised to the negative first power. What is this? 1/2, we get root 2 minus 1 minus 1 over root 2 minus 1. Man, how are we going to put all that together? We're going to come up with a common gosh darn denominator. So we're going to get 1/2 times the square root of 2 minus 1. So what we're going to need to do is multiply these things by root 2 minus 1. Top and bottom. So we're going to get root 2 minus 1 all squared minus 1. All times a half. So we have 1/2. I promise this will end eventually. Minus 2 root 2 plus 1 minus 1. All over root 2 minus 1. So those cancel out nicely. And what are we left with? We have 1/2, and then we have 2 minus 2 root 2's all over root 2 minus 1. I swear I made a sign error somewhere. Something seems strange. I think I committed a sign error somewhere. But I don't know where. Oh, well. Oh, because it's plus 1. I'm an idiot. I keep writing minus 1 and this plus 1. It's +1. There's my sign error. Sorry, I'm not remaking this video. We've come too far. We've come too far. There it is. Now we've got it all fixed. Now we got it fixed. Oh my goodness. Sorry about that, y'all. Now, if you just factor this, you turn this around, you get 2 root 2 plus 2 all over root 2 plus 1. I'll bet you there was a simpler way. My apologies. If you take out the 2 that's up top, times 2, you end up with root 2 plus 1 over root 2 plus 1. Those just cancel. You get 2 times 1/2, and the answer is just 1. Oh my gosh, I am so sorry for such a long video and the mistake in there. My bad. My bad. We all do silly stuff sometimes, and I did. This is a horrible worst case scenario, but I want you all to be aware of the fact that hyperbolics exist. But I sure as heck did not want to make a 16-minute video, so my apologies for that. We are done with lengths of curves. We'll go into surface area. That's a real short section. We'll only do just a couple, and then we're just going to move right on from there. All right, take it easy.